Please welcome Brent Stevens, and he's going to be talking about some research he's done on ozone infiltrating through the envelopes of homes.
Before I get into my actual research, I'm going to spend a little bit of time talking about air pollution in general. All right? I'm going to talk a little bit about outdoor air pollution and a little bit about indoor air pollution, sort of in a broad sense. And then I'll get into the research that I've done relating to air pollution inside homes, specifically homes around Austin. So what do you think of when you hear the word air pollution? You know, what are some terms that come to mind? Smog. Multiple smog. All right. Chemicals? Yeah. Ozone. I guess we just gave you that one. Ozone, definitely. Well, good. Well, let me tell you a few things that I think of when I hear the term air pollution, and I think you've named some there. I think of power plants, emissions from power plants. I think of traffic. I think of smog, especially smog in large cities. I think of people in Beijing riding bicycles with face masks on, right? But I think of a bunch of other things too when I think of air pollution. One of the first things that comes to mind when I think of air pollution are actually trailer homes. There's a picture of FEMA trailers, which were found to have large amounts of formaldehyde and other VOCs, volatile organic compounds, inside them that cause sort of sensory irritation, things like that. And these were given to victims of Hurricane Katrina, right? I think of tables. I think of furniture sometimes. I think of pressed wood products like this, which have been shown to emit formaldehyde indoors. When I think of air pollution, I think of kitchens. I think of gas stoves. They emit particles and nitrogen dioxide into the air, and emissions and use and ownership of gas stoves has been associated with a range of sort of respiratory health effects, irritation to asthma. I think of freshly painted bedrooms. That sounds scary, but I think of freshly painted bedrooms, you know. Especially when they're first painted, they emit large amounts of several kinds of tons of kinds of organic compounds, VOCs, you may have heard. They generally sort of emit in large amounts and they decay over time as they emit off the walls. Exposure to VOCs indoors has been associated with asthma in young children and other respiratory issues. When I think of air pollution, I think of these things, air fresheners, scented products, things like that. These emit all kinds of organic compounds, and use of chemical household products has been associated with respiratory symptoms in children and even the development of asthma in adults. So when I think of air pollution, I also think of lipstick. I think of personal care products. I think of shower curtains. I think of plastic things. I think of shampoo and conditioner. I think of little rubber duckies. These contain plasticizers to make them flexible so they can serve their purposes. But that also emits a class of compounds known as phthalates indoors, and a phthalate exposure has been associated with respiratory systems, development of asthma, and allergy. I think of old lead paint in old buildings, you know. Lead paint was phased out years ago, but in some old buildings it still exists. Lead paint's been linked to intellectual impairment in children, even at really low levels. When I think of air pollution, I think of these guys, cockroaches. Cockroaches release these tiny little particles into the environment, and exposure to those allergens has been associated with sort of asthma symptoms and allergy symptoms as well. Last, when I think of air pollution, I think of this guy. I think of people. We shed our skin every 2 to 4 weeks, completely shed our skin every 2 to 4 weeks. So we pollute, we smoke indoors, we stink, we sneeze, we distribute viruses, you know. So when I think of when I think of air pollution, I think that it's an indoor issue and it's an outdoor issue, right? There are many, many indoor pollutant sources of all kinds, wide range of health effects, a lot unknown, a little bit known. Outdoor pollutants also can infiltrate indoors. We know that. And then since we spend most of our time indoors, Studies show about 90% of our time indoors on average, some more, some less, nearly 70% of that time at home here in the US. Because we spend so much time indoors, our exposure to air pollution often actually occurs indoors, air pollution of both indoor and outdoor origin. Now the health effects of indoor exposures are sort of tough to get at. The connections are a little bit difficult to make, and they're expensive. That's the hardest part, they're expensive. It's expensive to go into someone's home and measure whatever's there, and then do that in thousands of homes and wait for people to report asthma symptoms or something like that. It's very expensive. We've made a good amount of connections between adverse health effects and outdoor pollutants, but we need to advance the knowledge of indoor exposures and health effects. And that's what my research is motivated by, and that's what a lot of people in our research group at UT are motivated by. So my actual research sort of begins with outdoor pollution. Outdoor pollutants are regulated in much of the world. Here in the US, they're relatively tightly regulated. They're regulated in most part by the National Ambient Air Quality Standards. Okay? EPA came up with these after Nixon signed the Clean Air Act in 1970. And what this does is set limits for 6 criteria pollutants. So of all the pollutants in the world, six pollutants are regulated outdoors. Those are carbon monoxide, lead, nitrogen dioxide, ozone, particulate matter, and sulfur dioxide. And these air quality standards basically set a cap for the outdoor concentration in your area. If you exceed that, your county or whoever's in charge will have to sort of go through the process of lowering those, and that's expensive. You might face penalties as well. So there are caps on these pollutants, and for the most part, these pollutants since 1970 have come way down in most areas. A couple of pollutants that still exist and are still problematic for really locations where millions of people in the US live. So I forget the numbers, but when you look at ozone and particulate matter, in a lot of areas in the US, they still reach levels that are near or exceed, sometimes frequently, mostly infrequently, the air quality standards. So they're lower, but they still present a health effect. And so these are 2 pollutants that I focus on and primarily in my research. So I want to first talk, still not even getting into my research yet. I want to first talk about sort of the background information and health effects of ozone and particulate matter, all right? So ozone is kind of a funny compound. Someone named that earlier when they thought of air pollution. Ozone, the basic way to think of ozone is that it's good up high, but it's bad nearby, okay? What I mean by that is in the upper layer of our atmosphere, the ozone in the ozone layer blocks harmful UV light from coming in and essentially baking us, So we need ozone up high. But once it's down low in the troposphere, it's a primary contributor to smog. Ozone's really reactive, so it's harmful to humans, it's harmful to buildings and the look of buildings, and it's harmful to plants, all right? And ozone is kind of odd. It's a pollutant, but it's not directly emitted by many sources, hardly any in the outdoor environment. Ozone is actually a product of other pollutant emissions. So it's actually, this is a gross oversimplification, but it's essentially a photochemical byproduct of a bunch of reactions between atmospheric oxygen, emissions of VOCs, nitrogen oxides. Those last 2, VOCs and NOx, are emitted from things like power plants and more so vehicles. Combine those with sunlight and produce ozone. So ozone's kind of weird. To regulate ozone, you actually have to regulate its precursors because it's a byproduct of a reaction. So this is an oversimplification of a bunch of complex photochemistry, but that's the basic deal. Now, particulate matter is kind of, it's another class of pollutants. It's really, the study of particles it's an entire field on its own. I'm a member of the American Association for Aerosol Research. Essentially, people that study particles, whether they're delivering tiny particles of drugs or they're combating air pollution. So particles are emitted directly from vehicles as combustion sources, emitted from power plants. There are also a bunch of natural sources of particulate matter. Does anyone recognize this photo? Yeah. This is Labor Day of last year, the Austin skyline with the Bastrop wildfires sort of raging in the background. Tons of particulate matter. In fact, wildfires are a big contributor to our particulate matter levels across the world. Now, particles are essentially little solid fragments suspended in air. They can be little aggregates of soot or carbon-containing particles. They can be condensed matter. They can be metals. Particles can contain metals. Particles can be carriers of other particles. Here's a picture of I think a diesel soot particle carrying a small fragment of an allergen, a cockroach allergen, or maybe a mouse allergen, I forget. But particles exist in a wide range of sizes. They span several orders of magnitude, down to about a billionth of a meter, a nanometer. Most of this is invisible to the naked eye, up to 100 microns, or 100 millionths of a meter. Larger particles, when we breathe them in, generally deposit in our sort of nasal cavity. Sometimes big ones are blocked by our nose hairs, or at least in our upper respiratory, very far upper part of our respiratory system. Now, really small particles are deposited in what's generally called our upper respiratory system when we breathe them in. And then these in the middle are actually a little bit harder. They're not a little bit harder to capture on a lot of filters. And they actually don't deposit in our lungs until they reach our lower respiratory system. They're not dominated by all the forces that impact particles and make them deposit. So these can actually enter our alveolar sacs and go directly into our bloodstream. Okay, so the size of particulate matter is really important for different health effects and how they interact in different environments, whether it's outdoors or indoors. Composition is also important too. And I'm not actually even going to talk about composition of particles, what they're made of. I'm not even going to talk about that today because I haven't done those measurements. But essentially, large particles consist of things like full grains of pollen, large bits of dust and fungal spores. And down at the other end, particles get so small that they almost become the size of gases. And then in the middle, we have things like tobacco smoke, diesel smoke, and viruses in this sort of harder to capture range. So that's just kind of an overview of a little bit about particulate matter. So when it comes to measuring particulate matter, we have several instruments to do this around our labs. We can count them. There are instruments out there that we can count particles one at a time, a lot at a time, any particle less than X size or whatever. We can count them in size resolved distributions. That is, there's X amount of 10 nanometer particles, but Y amount of 20 nanometer particles. We can weigh them. We can take a big sample of air and weigh everything that's suspended in there. We can lay out a sheet and measure everything that deposits onto our little sampler and weigh that. Or we can sample a volume of air and put some devices sort of upstream of the sampler to cut off particles. Say, only particles smaller than a certain size will enter in here to our sampler. So we often do that. We measure the mass of particles with diameters less than 1 micron in diameter, or 2.5, or maybe even 10. And these two in red, PM 2.5, which you'll hear me talk about a little bit more, and PM 10 are usually what's regulated by those national air quality standards. So in Austin, they're measured. In a few places, I know they're measured up around, I think, Far West Boulevard. And those are the, especially PM 2.5, those are the concentrations, or the types of particulate matter that we have max concentration limits that we don't want to exceed. Now, when it comes to outdoor ozone and particulate matter, these two pollutants that I'm focusing on, we have lots of studies that show when these concentrations go up, people suffer health effects. I feel like I'm being really morbid, but this is how it is. So when we have lots of studies showing that when particulate matter concentrations go up, people suffer more respiratory systems. They die from heart conditions more often, more cases of lung cancer. When ozone goes up in an area, people are admitted to the hospital more often, suffer respiratory illness, and the risk of sounding morbid, die more often. So Those are made with outdoor measurements of these pollutants. But like I said, we spend most of our time indoors. And then we know that outdoor, although not very well, we know that outdoor particles and ozone can both infiltrate into buildings. So therefore, our exposure to particulate matter and ozone, and in the case of ozone, ozone is very reactive when it comes indoors. It reacts with a lot of things, and there are a lot of harmful byproducts. So our exposure to outdoor particles, ozone, and reactions of ozone byproducts in particular often occurs indoors. Here's just a couple of snapshots of the types of studies. I find these interesting, but the types of studies that are on a large scale that link outdoor air pollution and health effects, specifically mortality. So what this shows is a study about 5 years ago where these researchers measured ozone on today and the day before, took the average of that in almost 100 cities in the US, and plotted that versus the risk of increased mortality, so the increased rates of death in the population. And they go up a little bit. Not huge, a couple percent, but they go up a little bit when ozone goes up. And this is a similar kind of graph of the risk of mortality in 6 different communities. This is from a landmark study back in the early 90s that measured PM 2.5 concentrations outdoors in 6 cities from Topeka, Kansas to Steubenville, Ohio. Plotted that versus the risk of mortality increasing, and they saw this pretty strong relationship. Cities that had higher levels of outdoor PM 2.5 concentrations had a higher rate of deaths. So these are the kinds of studies that motivate our outdoor pollution air quality standards. Same sort of thing, same sort of studies for something a little less morbid, but still an issue. The number of ER visits for children with asthma symptoms. Again, for ozone and particles, the same deal. The risk versus the outdoor concentration. Same sort of thing. You see increases. All right. So these are what drive our air quality standards. Just to maybe bring it home a little bit, I went to TCEQ's website and downloaded data from last year for ozone and particles, PM 2.5 in Austin. And again, I think these are measured over off Far West Boulevard. But what I'm showing is the daily mean outdoor ozone concentration. So the average ozone concentration throughout 2011. You can see we have, here in Austin, we have a baseline in the winter of about 20 parts per billion. That increases in the springtime up to, I don't know, 40 or 50 parts per billion on average for the day. And then it actually drops off beginning in May. Does anyone have any thoughts of what might be causing that? UT, basically. Yeah. UT and maybe the entire school system, really, because a lot of, remember ozone is a byproduct of reactions of NOx and VOCs, which are emitted primarily from vehicles. So take the vehicles off the road, drop the ozone, right? And then everybody goes back to school, right? So that's what our profile looks like. When we overlay the air quality standard sort of limit, it's measured in a funny way, but it's just basically to meet the air quality standards. I actually forget now, and I think they're changing it. You can't exceed 75 parts per billion more than 4 days over 3 years or something like that. But if we look at these gray bars show the standard deviation from the mean of each day. You can see we, here in Austin, maybe a couple of times a year, we'll get up near the regulatory limit. Usually only 5-10 days a year, something like that, which is why you might have seen some signs like this. Know before you go, high ozone possible, check ozone levels, Austin Parks and Recreation, right? Maybe you've seen this around the trails or maybe on the nightly news or something saying, hey, please try to carpool tomorrow or something like that. Limit your vehicle emissions to keep ozone down. And if you're a sensitive individual, a lot of times you say, go inside, just go inside and try not to do too much activity and increase your breathing rates when ozone's high. So ozone, it's an issue in Austin. We're near the regulatory limit a lot of times, always sort of dancing around that. We're not nearly as bad as places like Houston and Los Angeles, but it's an issue. Now, particulate matter is a little bit less of a story. Here we have the same sort of graph from TCEQ, the daily mean PM 2.5 concentration for 2011. And if we overlay the air quality standard, again, we reach it every once in a while. So not a huge issue, but a few days, maybe several days a year, we'll actually get near some regulatory limits. So that all finally leads into the objectives for my actual work. That's what everyone else has done. The objectives for this work, I hope are kind of coming clear a little bit, but they're to focus on indoor exposures to outdoor pollutants, and I'm looking at particles and ozone. Now, when it comes to this kind of work, measurements of outdoor pollutants are relatively limited to date, and part of that problem is there aren't many people doing them. They're also non-standardized, they're invasive, as you'll see in a few minutes, and they're costly. They just cost a lot to do. So a few methods in the academic literature exist to measure how particles infiltrate indoors, but no one's ever measured ozone. No one's ever measured how ozone infiltrates indoors. So the objectives of my work in the last sort of stage of my PhD work have been to develop methods to measure the infiltration of ozone and particles and apply them in an unoccupied test house that we have out at our research campus. And once we got the methods all sort of ready to go, then I went out into a bunch of homes around Austin. And what we were trying to do was characterize the buildings and essentially assess implications for exposure to these two pollutants. So when we think about particles and ozone infiltrating through building envelopes, we can think of it in this little box diagram of a house where we have outdoor particles and ozone. Now we can write what's called a mass balance on the house. This is about the only equation I think that you'll see, but we can write at steady state conditions, it's sort of an average condition, we can say that the indoor to outdoor pollutant ratio is equal to that which penetrates from outdoors or infiltrates through the building envelope from outdoors, divided by what's lost by removal by air exchange. Air exchange rates are the rate of turnover of air in a building, plus whatever's lost by indoor removal. Particles are removed indoors by landing on surfaces and by being controlled by HVAC systems and filters. And then ozone is a reactive pollutant that I mentioned. It's lost indoors by deposition, reactive deposition to surfaces, reacting with other compounds, and then also reacting with filters or HVAC ducts or something, and surfaces within the HVAC system. So all these three parameters are important for determining the amount of outdoor pollution that comes indoors. The parameter that I most care about, that I've been measuring, is this parameter P. It's called a penetration factor. And what that is, it's sort of like an efficiency. It's a value between 0 and 1 that we're going to measure and assign to the building envelope, so just the exterior shell of the building. If P, the penetration factor, is 1 for either one of these pollutants, the envelope offers no protection. Whatever's outdoors comes right indoors. Nothing's lost at the building envelope. Now, if P is equal to 0, the opposite occurs, and the envelope offers complete protection. So this source term up here goes to 0. You have no outdoor pollution indoors, right? So that's the parameter that I've been most trying to measure, and it's surprisingly sort of it takes a PhD to go measure this, apparently. But so first I'm going to talk about ozone infiltration or penetration. I'm going to talk a little bit about the test method and results from 8 homes around Austin. So here's the basic test method. I show up to a house, and I take my little ozone monitor, I set it up outdoors, and I measure outdoor concentrations. And then I go inside, and I actually have to emit some of this. I have to generate ozone. I actually have to emit my pollutant. You have to pollute to decrease pollution or spend money to make money or whatever. But anyway, I go inside. No one's inside. I start emitting this pollutant to levels 5 or 10 times higher than they are normally indoors. And then I actually leave the building. I set my monitor up where I can actually see it. And once it goes to a high enough level, I run back inside. I shut it off. And I close all the doors and windows, and I leave. And I let it go for 45 minutes or an hour or something like that. Then I come back, open the door, shut everything off, get another outdoor reading. And what I can do is take this decay, because we need a big change in the data, because we need to be able to measure more than one thing using just one equation. So we can take this decay portion and solve for those parameters that I was just talking about. I can use a tracer to solve for air exchange, I can solve for the loss rate, and then ultimately the penetration factor for ozone through the building envelope. So I took this test, I performed it a bunch of times in our test house. We have a little manufactured home out at the Pickle Research Campus at UT, which is about 8 or 10 miles north of the main campus if you haven't been out there. So this is where we can kind of refine our experiments before we go bug people and kick people out of their homes and that sort of thing. So then I went to these 7 homes around Austin, a total sample of convenience, since you have to convince people like Susan to let me in their home for a couple of hours and fiddle with their house. So I'm indebted to these folks. So went around to these 7 homes, and here are the results. So these are the first ever results of ozone penetration factors through building envelopes that I'm aware of in the world. So what we can see is the ozone penetration factor versus the test house in each of the 7 field sites. We can see basically what to take home is that penetration factors for ozone range from a low of about 0.6 to a high of about 1. That's your house, Susan. Yeah, it's like a garage apartment. So basically what that means is that at best, the most protective house in our relatively limited sample of only 8 homes blocked about 40% of outdoor ozone from coming in. 60% came through. And our worst house, Susan's, only in that sense, didn't do anything to buffer against outdoor ozone. And so to take the average of these, on average about 80% of ozone penetrated through building envelopes in these 8 homes. And that's new and novel because that's normally been assumed to be 1, because no one, 100% comes through, no one else really knows. So we made these first measurements. So the average is interesting in that it's lower than what people normally think. But the differences between the homes are, I think, what's even more interesting. So with, again, a very small sample of only 8 homes, but we were able to look in the data and see if we can explore the results to maybe learn something, what impacts ozone infiltration. And I think that the 2 most interesting relationships that I found were that the ozone penetration factor that we measured was significantly and positively associated with some scatter with the fraction of painted wood on the exterior envelope. Now, that makes some sense, and I was actually tracking that because some materials are much more reactive with ozone than other materials. Painted wood in lab tests has been shown to be not as reactive with ozone as something like brick or stone or whatever stone is on these walls. So it might make sense that if you have more brick or stone, so down on the left part of the graph, versus more painted wood, ozone would have less to react with as it came through on this end of the graph. So it actually wouldn't be diminished by the envelope. So it makes some sense, but again, we can't take it for too much because it's only 8 homes. We need to do these in a lot more homes. The other interesting relationship was that the ozone penetration factor was significantly and negatively associated with the year built. That's even easier to measure than trying to figure out how much painted wood is on a building. So basically what that shows is that newer homes in our sample, ozone penetrated less efficiently through the envelope. And that makes some sense because newer homes are tighter. There might be less holes essentially in the envelope for ozone to infiltrate through. Older homes are generally leakier. So it makes some sense. And these are the first kind of findings to maybe suggest that, maybe if we do enough of these, maybe if we go into 50 more buildings or something like that, maybe we'll never have to do these silly experiments again if we can find these sort of correlations. So, so that's it for ozone infiltration into buildings. I'm going to now switch to the measurements we've done measuring particle infiltration into homes, and we've done a little bit larger study here. So the test method basically involved taking these little particle counters that we have in our lab and going to a bunch of homes yet again. The particle counters that we use, they're not perfect, but they measure the total number of particles between 20 nanometers and 1,000 nanometers, or 1 micron. So basically what that means is they measured particles in the size range of diesel smoke and tobacco smoke. So diesel smoke, being an outdoor pollutant, is probably the most relevant. So these are relevant for health. It's in that range that's kind of hard, that's hard to prevent particles from depositing deep in your lungs. So they're relevant for health impacts potentially. So here's the same kind of graph as before, but this time for particulate matter. And this is sort of a visual representation of our test method. So we're looking at the particle concentration versus the experimental time. These experiments lasted a little bit longer. I think this is one of the shorter ones. It took about 2.5 hours. But basically what we do, or what I do, is show up to a home and set up a particle counter, one inside and one out. The outdoor particle counter would continue measuring whatever outdoor concentrations do. We can't control those. Those just do what they do. Now, I manipulate the buildings a little bit to cause a big fluctuation in indoor concentrations. The way I do that is when I first show up to a house, I open all the doors and windows, or a couple of doors and windows, and get this huge amount of turnover with outdoor air. So I replace whatever indoor particles used to exist with whatever exists outdoors. And what that does is give us a constant kind of aerosol to measure, and it also elevates the indoor concentration near what it is outdoors. And then I shut all the doors and windows, close the place up, I turn on the HVAC system, leave the filter installed, and I leave the house for 2, 3, 4 hours at a time. So again, you gotta have willing homeowners that'll let you take over their house for 4 hours a day or something like that. But what would happen when I left is that particle concentrations would decay from their initial sort of artificially elevated level. They decay because they deposit on surfaces and they are controlled by the HVAC filter. They decay to this background level, and at that point, whatever happens indoors is due to whatever infiltrates from outdoors. So we can use this first part to solve for how quickly particles are lost in an environment, and then take those numbers and use all of the data to finally solve for this penetration factor. So it's that same parameter that we were measuring, but this time for particles. So went around to 19 homes this time, went to the test house and then 18 homes around Austin. A little bit larger sample, many more nice people let me in. And here are the results from these 19 homes, where one is the test house and those are the 18 field homes. So basically what we see is a little bit bigger range in these 19 homes. We see at a low end, Site 15 over here had a penetration factor a little bit less than 0.2. That means that only a little bit less than 20% of outdoor particles snuck through the building envelope, and about 80% were blocked at the envelope. So that's a very protective house. I don't think Susan's house is the worst this time. No, it's not. I think you're 4, but I forget. Wait.
8.
You're 8. Yeah. Yeah. No, yeah. Yours was one of the lower ones. Anyway, so sort of at the high end with Site 5 here, had a penetration factor of a little more than 0.7, which means that more than 70% of outdoor particles came through, and about 30% were blocked at the envelope. So again, when we take the average of these, the average is about 50%. About half of particles come through on average, and about half are lost in the envelope. And again, these data are great on the whole, but they're also interesting to explore in more detail. So again, we had a larger data set that we could approach this time to kind of explore the results. And I'm just going to show you a couple of relationships that I thought were particularly interesting. We found a few more. But again, I'm going to go back to the year of construction of a home. Can we learn anything from that? So first, I'm going to look at just this particle penetration factor that we measured that I just showed you. And if you plot those versus the year built, we get a decent relationship. It's not incredibly strong, but in general, newer homes had particles penetrating through their envelopes a lot less efficiently than older homes, right? Now, if we look at the same sort of plot, but for the entire outdoor particle source term, if you remember from that image of the house, where we have the penetration factor, which is also higher in older homes, and the air exchange rate, the rate of turnover of air through the building, which is also higher in older homes, the combination of those two is also higher in older homes, and we get a little bit stronger of a relationship. of the outdoor particle source term. So the rate at which particles from outdoors are being dumped into a house declines significantly with year built. So if you live in a newer home, you're probably more likely to be buffered against outdoor air pollution than if you live in an older, leakier home. So those are the main findings, but what does all this mean for exposure in the long run? So what does this mean for indoor exposures to outdoor ozone and particulate matter? Well, if we take our little equation again of the indoor-outdoor ratio for ozone and particulate matter, and we normalize all the houses in our study by assuming constant loss rates, meaning every home has the same loss rate. We'll just take an average. That means you don't have a better filter than he does, that sort of thing. And we look at the differences between the least protective home and the most protective homes. For ozone, our least protective home was built in 1920. It had a high penetration factor. This was actually my old house. Had a high penetration factor and a high air exchange rate. It was really leaky. So the indoor-outdoor ozone ratio in this house would be about 22%. Now, in the tightest, most protective home in our sample of only 8 buildings, remember, was our test house built in 2008. It had a low penetration factor and a relatively low air exchange rate. So its indoor-outdoor ratio would only be about 5%. Indoor concentrations would be about 5% what they are outdoors. That's a difference of a factor of about 4.5 between the worst and best home in our study. Now, a little bit more drastically, for particulate matter, the least protective home in our study was built again in the 1920s. It had a high penetration factor. It had a high air exchange rate, which means the indoor concentration of outdoor particles is about 32%. 32% indoors of what it is outdoors. The most protective home was built in 2011. It was a brand new model home up in Pflugerville. It had a really low penetration factor, and it had a really low air exchange rate. Its indoor-outdoor particle ratio would only be about 2% of what it is outdoors. So that's a factor of 16 difference between our worst performing home and our best performing home. So the ultimate story is that in some homes, indoor exposures to outdoor ozone and particulate matter are going to be a lot more important than other homes, and they generally trend with building age. So I'll leave it there, and I would like to acknowledge my funding sources, and again, the homeowners and occupants for volunteering their homes. I couldn't have done it without them. My advisor, and then I'll leave my email address and my website up if you want to jot it down and check out other publications or the publications from this work, or have any questions or comments. And I'll end with that. And I'm happy to take questions if you guys have any.
Brent, just a clarification. Did you say the painted wood was the best or worst?
Gotcha. The painted wood, since it's not very reactive with ozone, was actually the worst, in that when ozone passes painted wood, it doesn't necessarily react with it. So that it was the worst in our study. Again, a very small sample, but yeah. And the homes that had some significant fraction of brick or stone or even like a cement fiber that's more porous, in the lab studies, when ozone passes over it, more likely to react. So it might make some sense that more of it reacted at the envelope, therefore less came through. So.
What reaction are you talking about?
So there's a couple of different things. Ozone reacts either directly with sort of pores in materials. And I'm not a material scientist, but my understanding is that it either reacts directly with pores, so whatever the material is made of. It can be an absorption kind of mechanism, I think, in that it just tucks in these pores. There can also be, and this is something we don't know about, there can also be, if there's a reactive, if there's a compound that's coating a material or something like that, that can be more reactive with ozone. So people have shown in all kinds of indoor studies, for example, cooking oils, products of cooking oils, when they land on surfaces, you know how they get kind of sticky and gummy. Ozone loves to react with that stuff. So people have shown that, a dirty countertop versus a clean countertop, ozone will react more and create more bad byproducts, whether those are harmful or not. Sometimes they are, sometimes they aren't, but that's generally the view.
Do you have any intention of studying the reactive matter materials?
Yeah, I think so. I've mentioned I'm graduating, which means I've applied for a bunch of faculty positions, so I have to really start thinking about these things, right? And one of the things that we noticed in our test house when we did all these experiments was that when we repeated the ozone tests in the test house like 16 different times, and we tracked wind conditions around the house, and we noticed that when wind was from some directions more so than others, ozone penetration factors, when wind changed, ozone penetration changed. And we don't really know what's going on there, but it might make some sense. The southern sort of prevailing winds out at the test house, when winds were from that direction, ozone reacted more. So one thing that might be happening is that particles and all sorts of organic matter are constantly being deposited on the envelope, and ozone's likely to react with some of those, is sort of hungry for some of those things. So that might be causing it. So it's one of those things that, yeah, I've written into job applications that I'll maybe build an envelope structure or something and do different envelope constructions, foam insulation versus, cellulose or fiberglass, and trying to get the same airflow patterns, but see if something's reacts more or less. So yeah, that's definitely something that I'd like to see. And I think the especially on the particle side, the case of this brand new, super, super tight, it was a net zero energy demonstration home, having the lowest influence of outdoor particles. It's something. It's like we're accidentally going towards buffering from outdoor pollution more. So it'd be nice to know why. Yeah.
Okay. Did you look at the relationship between your peak factor and the ACH to see if there was, it looked like there was probably a directly proportional relationship, and with the ACH being a much easier number to get a hold of, you could end up using that as your factor as opposed to taking these measurements.
Yeah, no, we just finished up looking at those results, and yeah, they were correlated. I can't remember how well, but there was definitely a correlation, and it makes sense, right? Sort of leakier buildings had higher Ps and air exchange rates. So yeah, that's ultimately something. The whole point of, I really do think the whole point of this work is to never have to do this silly work again, So I think that's really something that we might be able to explore.
I just mean as opposed to the year of the home where you can have a fair amount of variation. I mean, sure, your leaves are going to be a lot leakier and all that, but if you could just do a simple test and get your ACH numbers, they correlate directly, and that would be less.
Yeah, no, and we actually just submitted a paper on the particle infiltration stuff, and the main goal that I actually didn't even show here is we did blower door tests in all those homes. So those are even easier to do than air exchange rate testing, because air exchange rate at least takes a couple of hours. You have to inject a tracer and watch it decay, and we found a really strong correlation there. So.
And you're using ACH 50 numbers?
I use ACH 50, ELA, the effective leakage area, normalized leakage, which sort of normalizes for the size of the homes, and that was the main deal. Particle penetration factors were not, they were absolutely associated with those, but you couldn't, the data were too messy. You couldn't just say, if I know one, I know the other. But the outdoor source terms, so the combination of air exchange rate and penetration, were both very strongly correlated with some of those blower door results. So, yeah, that's.
One more quick question then. So were you able to track any particulate matter or any other pollutants to see if ozone acts in an unusual way, or if it's or if the behavior of ozone tracks with the behavior of other?
Yeah, the one interesting potential answer there was that if you plot the penetration factor for ozone that we measured versus particles, there was no correlation. No correlation, yeah. But as far as other measurements, we didn't do. We were just focusing on the envelope. So, but a lot of those have been done, and some of the byproducts of ozone reactions are they're all over the place. Some of them seem really harmful. Most of them we don't know anything about. But, yeah. Do we have time for any more? We still have. Or is it?
Sure, a couple more.
Okay, sure.
My question has to do with the baseline test conditions. On all your homes, the 8 homes and 19 homes, I would like to know if you took into consideration the humidity, temperature, time of the day, and the sun exposure.
Yeah, that's a good question. I have, for the particle measurements, I have measurements of indoor and outdoor temperature and humidity, but I actually haven't marched through all those yet. The ozone measurements, we tracked indoor and outdoor temperature differences, relative humidity, and didn't find any correlations with anything.
How about from home to home, from sample to sample? Do you think that might have
Yeah, it could, especially something like if it had, one thing we meant to track and we still haven't, but if it rained the day before, maybe your envelope was, you know, soggy essentially and would react with ozone more. But it's a good question. I haven't explored it. Yeah.
Yes, if you were doing your testing, did you always have the AC off, or did you test with both conditions on?
We actually used the AC. We had the AC system running. Yeah. Just in the fan only mode, and mostly to just help with the well mixed assumption. There's an assumption in all this that the concentration here is the same as it is here, you know. And in most homes, it's a decent first approximation, but not good enough to get this kind of clean data. So we operated fans and ran the HVAC system. So, yeah.
Maybe we can take questions at the end.
Yeah.
Can I ask just a quick follow-up to that?
Yeah.
Did you, so in my house where there was no HVAC system.
That's right, all but one. Yeah.
So even the 1920, even your old house didn't have, had an HVAC system?
Yeah, yeah,
Okay.
yeah. Yours was the only one, which actually
Did you run the fan on the window unit? Or?
I didn't, and that actually might explain it. I need to. That might explain the high penetration because you have kind of an intentional hole in your envelope, you know. So that actually might explain it.
Yeah. Well, I was just thinking about that because one of the other things you mentioned during your presentation is there might be stuff throughout the duct system that the ozone could react with, and there wasn't anything for ozone to react to or stick to speak of in my house. So.
Your house actually had really high ozone deposition rates, and I think that has something to do with the volume of the house and the amount of surface area in a small volume. And also, you know, if you had just cooked or something like that a few hours before, it provides sort of a bunch of reaction sites. So that's, yeah, your house actually had quite a high loss rate, which is kind of interesting because that is intuitive, you know. People have shown previously that if you turn an HVAC system on, it's just more, there's more turbulent sort of mixing, and there's more places for air containing ozone to land and lose its ozone. But yeah, so should we?
Okay, well, we're going to switch speakers now. Let's thank Brent for coming.
Thank you all.